Welcome on the lecture on machine learning and bioinformatics. Yes. Okay. So this part we already started last week, and we arrive at a point where we studied some density estimation approaches, and we have seen some histogram, how to build a histogram. We tried them already, and then parametric approach. For the parametric approach, we used representation of the data in form of a Gaussian distribution, so multidimensional or multivariate Gaussian. Just to be sure, please remember that for the multidimensional Gaussian distribution, the density function is a little more complicated than the density function for one-dimensional. So for the one-dimensional, we have just standard deviation and mean, just two parameters for the normal distribution. But in case of multidimensional Gaussian, we need D is the dimensionality. We need not so simple formula for this exponent because we need variance metrics sigma and their inverse, sigma to the minus first power of the inverse for the covariance matrix. And here we have determinant of the covariance matrix. So it depends not on the independent dimensions, but between the dimensions there will be some relations. These are modeled by the covariance matrix. We will see such multidimensional Gaussian very often during the lecture, so therefore I am spending time on this again. And what we did last week was that we look at the different formulas, how to approximate the covariance matrix, and we arrived at this point. So we are able to compute estimate for the covariance matrix based on our data. And the data set, we'll go a little back to review the notation that we have some big data set, capital X, where one observation is one row of the matrix and one column of the matrix denoted by boldface X, lowercase, denotes the value for one attribute for all the observed data, for all observations. Okay, and but sometimes the situation is little simpler, and in case that we have such data that there are no dependencies between dimensions, between attributes, then the covariance matrix is much simpler because it has zeros elsewhere beside the main diagonal. And on the main diagonal, we actually have squares of standard deviations for each dimension. So in that case, it's simpler, much simpler, because it's easy also to compute the inverse for such metrics. How will look like the inverse for this matrix? Just to be sure that it's simple. This should be a matrix that if I multiply the covariance, the matrix sigma with the inverse, I should obtain the identity matrix. No, 1 divided by square of the standard deviation. It's so simple. So And even further, if the data are orthogonal, so the dimensions are independent, and homogeneous. Homogeneous means that the standard deviation in each dimension is the same. So sigma 1 till sigma d is the same sigma. Then we can write the covariance matrix even simpler. So it's sigma squared times identity, and then of course the computations will be even simpler. To estimate the covariance matrix, we just compute the means, which is easy, means per columns of the observation matrix, and for computing the standard deviation, we can use the formula for approximating the for the sample standard sample. This is formula for sample variance here, but we know that all the columns represent different dimensions are orthogonal, are independent. Then we can compute the sample variance for each column. This would be here 1 divided by n-1 times the sum of value minus mean squared. But we will do that for all d columns. So we divide it by d. So this will be even better estimate for the standard deviation. But this is with this very strong assumption that the dimensions are orthogonal and the variance or the standard deviation for each dimension is the same. So this is very strong. Usually we don't have such guarantee. Let us switch to second part, to parametric approaches. For parametric approaches, we suppose that the distribution of the data can be modeled to some specific form, specific in sense. We suppose, for example, that the data is described by given distribution. For the distribution, we need parameters which describe the exact form for the distribution. The main problem with such approaches is that we assume that the data have some properties. For example, if we assume that the data have a simple distribution, which is something similar to normal distributions. So such distribution is called unimodal. There is only one local maximum. But if in reality, if actually the data are distributed with two modes, then the approximation will be in general very long. So this is hard to obtain reliable results if we don't have any additional information about the data. Much simpler approaches are non-parametric. What does it mean? So we doesn't infer any assumption on the data. We don't know what is in the data, but we still would like to build some reliable model for the density of the data. And for that we can use, for example, local density estimators. So when we look at some point of the space of possible values, we would like to know the value of the density function. If I suppose that you remember the meaning of density from physics, from the physical world. Density is the property of matter. How dense is the matter? And here we can estimate the density in some smaller region of the space, and in the following way, we count the number of our sample data. We have some sample which fall within this smaller region, divided by the volume of the region, capital V, and divided by the capital N. Capital N is the number of observations. So such value can be used to approximate the density in the smaller region of volume capital V. Based on that, we can use two different methods: kernel approach and K nearest neighbor approach. Kernel approach is very easy. One of the problems of the histogram approach was that if we build a histogram, then we approximate the density function or approximate the density based on the histogram. We obtain a function which is not continuous. And we can easily obtain an approximation which is continuous by using some function called kernel function, and for each point of the observation, if it would be in one dimension, so we have distribution of the points, and for each point we can say, okay, if it would be this one point, if it should define some density. So the density should be highest at the point and small farther from the point. So for this point, the density function could be, for example, a bell-shaped curve with integral with the area under the curve equal to 1. If we would have just one. We have many points, so for each point, we add such bell-shaped curve, need not to necessarily be the bell-shaped curve, or some curve, which has the area under the curve equal to 1, and we sum all these functions together. Of course, for each point, we have some function which is area under the curve equal 1. So, and we have capital N points. So the integral, the area under the curve, after summation, sum will be capital N. We would like to have an estimate for the density. So therefore, we divide it by capital N. And this is exactly what is written here. So the density function is approximated to 1 divided capital N, and sum of the functions, so the kernel functions, rho sub I, x. X is the point we would like to approximate. So this is a new point, and for this point we would like to know the density. So in this point we compute the sum of these kernel functions for all input, for all training patterns, or for samples we have. And rho sub I, as is written here, is the similarity, similarity between uses the similarity between x and ith sample point, and transform it using some function. And the function here used is something which strongly resembles multidimensional Gaussian density function. But this is not exactly. Why this is not exactly the multidimensional Gaussian? So we have here the multidimensional Gaussian density function. It's too fast, faster than my computer. So you can see here 1 divided by square root 2p to the d's power. D is the number of dimensions times the determinant of the covariance matrix. And here is e minus xi minus mu. So it's we subtract the mean, and here we have the inverse for the covariance matrix. So this is similar to the distance between x and the mean, or the mean, better the expected value, x minus the expected value squared, divided by 2 times the variance, sigma. Here we use the inverse matrix for the covariance matrix and divide by 2. And what is used here? We have here 2 pi times h square to the d divided by 2 power. So this is the square root of 2 pi h squared to the d power. So instead of the covariance matrix, here we have just one value h, and here we have also just the value h instead of this inverse of covariance matrix. But the interpretation is not so bad, not so hard, because actually this corresponds to the situation where the Gaussian is the multi-dimensional Gaussian distribution is used in case of multiple dimensions and homogeneous with the same variance. In that case, the density function can be expressed in such simple form. So why is this so complicated? Because we have d-dimensional vectors, and what we use here, actually, according to this formula, we use such Gaussians, but d-dimensional and homogeneous and orthogonal. So what's the meaning? If, for example, if it would be in 3 dimensions, this would correspond to some sphere in the 3-dimensional space. So we add for each observation. So for each observation, we create such d-dimensional normal distribution around each point. We sum them together and divide it by the capital N, the number of observations we have. And this is the density. On the right hand side, there is an example. If we use a very narrow h, so small h, and we have here observations, then we obtain such approximation. The approximation is the blue line, where the real distribution is the green one. If we increase the size for h, we can obtain an approximation which is quite similar to the desired distribution, desired density. And if we select h too big, then maybe we will miss completely the distribution. Okay. This was one approach was this kernel function. Second approach is k-nearest neighbors. K-nearest neighbors is very often used in many different machine learning settings. It's very simple. Usually, I suppose that you know the application where it is used for classification. So if I would like to know how to classify a point, I will find k neighbors, k closest points in our observations, and look at the most often classification, and this will be assigned to the point. Here we use also the approach of k nearest neighbors to approximate the density. And it's quite interesting because we select k, capital K is the number of neighbors. And if we have one new point, we find a sphere around the point which contains exactly k neighbors. Of course, if some region of the space was not covered by the samples in our observations, then we need to take bigger sphere. And on the other hand, if it is in some region where there are many samples, then we need just small sphere in order to obtain to contain k nearest neighbors. So the approximation for the density will be k divided by capital N divided by the volume of the sphere containing these k closest neighbors. So if it is more dense, then the size of the sphere will be lower. Otherwise, it will be bigger. So. And here is the example how it can look like in one-dimensional setting. So for one neighbor, so if we look just for one closest neighbor, we can obtain such a little strange approximation for the density function. For k equal 5, it's much better. For k equal 30. We obtain quite different distribution, quite different density. So all these approaches require proper setting of the number of neighbors. Similarly, as for the kernel approach, we need to set the size for the kernels. Semi-parametric approach is the fourth class of method. We assume that the data are generated from some models, for example, with M Gaussians, and why it's semi-parametric. Semi-parametric is in the sense that for the region we use parametric models, the number of regions are non-importance. And must be found from data. So if we assume that we can model it using capital M Gaussians, then how to combine them? So we have the Gaussians. They will be described by means and standard deviations. And of course, these are multi-dimensional, so standard deviation is not enough. We must use covariance metrics for each of them. And we have M such Gaussians. So we cannot easily sum them up, because by summing them we obtain density, which would have the area under the curve of size capital M. So we need to combine them better, and so we assign some weights W sub M, which weight the contribution of each of these Gaussians. And we require that the sum of the contributions will be 1. Why to use this? Because in this way we can say, okay, according to our observations, we have many data in this region and new data here. So we say, okay, this is more often the data, and this is less frequent. So for this cluster, we assign a bigger weight. For example, value 0.8, and for this, just two times. And in this way, we try to better model our observed data. Of course, for finding the parameters for this, the first cluster will be described by one Gaussian, and the second by second Gaussian. And the resulting density, so approximation for the density function, will be weighted sum of these two Gaussian density functions. So this is actually written here that it is the Gaussian d-dimensional. So here you can see the d, and here we need the covariance metrics and so on. For obtaining such, for finding the parameters for such Gaussians, usually it's used EM algorithm, expectation maximization. It's not explained here. Sometime in some later lecture, I will give a little more detail to the procedure, how to find such parameters. Questions? Because now we will switch to next section, and it's dimensionality reduction. No questions? Okay. So let us continue with the dimensionality reduction. So why we need dimensionality reduction? We can reduce complexity of the problem. So if the data is described, let's say if we have some microarray data, so we have thousands of attributes for single observation. And it would be convenient if we could reduce the size of the number of attributes to some small number. It of course reduces space complexity. We need less parameters for describing the data. It can save costs of observing the feature. Maybe some of the features are useless, so we don't measure them. Don't need to measure them. Less attributes can enable to develop models with lower number of parameters, and lower number of parameters usually means more robust models. So better interpretation. If we should interpret our resulting model, then if it is described by a small number of attributes, we can try to do that. The description contains several hundreds of attributes, so it's incomprehensible for a human to work with that. And similarly for data visualization, so this is also the goal, how to interpret, how to present the data for humans. We usually need just 2 or 3 dimensions. In general, we would like not automatically have one-to-one mapping, which will map the original data, original observation, which has many attributes, to some other data with a lower number of attributes. As I said, one-to-one, but this is not usually the case that we have such one-to-one mapping. And the original points x sub n is one row of this big observation matrix capital X. We would like to map to some detailed dimensional space. Y sub n is the mapping of x sub n. And for visualization, we need at most 2 or 3 dimensions. What is more important, can we use any such mapping for dimensionality reduction? It would be easy. There are infinitely many transformations for big dimensional, many dimensional space into lower dimensional space. Can you send me some simple transformation? How to obtain from 100 dimensional space, 1 dimensional description? Just take the first attribute. We have mapping. This mapping is not one-to-one, and maybe usually would like to have something like this. If x sub m is the nearest neighbors of x sub n, so we have this big observation matrix, and x sub n is one row of the matrix, x sub n is another row of the observation matrix. And if we know that xm is the closest to xn, then we would like, after the transformation, that the transform value n is transformed to yn and xn is transposed to yn. We would like that although one sub n will be the closest neighbors to y sub n. So it preserves the relations of distance. There is a problem how to define the distance. But in some settings, the distance is computed easily. For example, like some Euclidean distance or some other distance measure. But this property that the nearest neighbor should be mapped to nearest neighbor is the most important. So let us look at some methods. So the easiest one is the feature selection. Feature selection, it resembles the method that we select the first attribute as the representative. So we choose out of the d dimensions. So our observation has observation matrix has 3 columns. We select just k, smaller number of columns, and we say, okay, we will approximate using just these k attributes. And the remaining we ignore. The second set of, we will look at that on the next slide. Second approach is feature extraction. Feature extraction means that we compute new features out of the original features. So we have many features in original observations, and we combine the features here in order to obtain a lower number of features. There are many such algorithms, and here is some short list: principal component analysis, linear discriminant analysis, factor analysis, multidimensional scaling, but these are not all. On the slides, I will have at least two more methods. So let us look at the feature selection. So subset selection algorithms, this is a group of algorithms, not only one. It's extremely simple. Here we have 3 approaches. The first one is forward search. So our goal is to select a subset of the columns, subset of the features to represent the data. So for d features, we have 2 to the dth power, the number of all possible subsets. And our goal is to select some of such subsets. Forward search works with the following idea: add the best feature at each step. So we start with empty set of features, and at each iteration we try to find the best new feature. How to find the best new feature? So we take our current set of features, we add one of the remaining columns of the matrix, and we compute the error of the approximation. How to compute the error of the approximation? This could be different. For example, if we know that we would like to use the data for classification, then we fix the classifier, the method for the classification, and we supply the classifier with extended set of features and compute the error of the classification. And we select such attribute for which the error will be the smallest one. So J is the index of the column we would like to add. J. So this means that.
No, I know, but at the last line of the algorithm, it says that we should add xi, but we want to add xj.
Xi, this capital Xi is the whole column, and therefore, yes, xj. You are right. You mean here is the error. Excellent. Thank you very much. I will correct that. I don't understand you probably directly, but you are right. So we must add the x sub j, you are right, and we will add it to f and repeat the iteration. Of course, we should stop at some point. If we don't stop, we add all the attributes and we have done now no dimensional reduction. This method is hill climbing. Why? Because we look for the adding the dimensions which reduces the error in maximal way. So we select one attribute. Of course, this method need not to be optimal. We have no guarantee that we select subset which reduces the error at most. Why? Maybe if we combine several attributes, we could reduce the error better. But using this method, we will avoid one of these attributes for which the combination is optimal, and we obtain something which is not optimal. The problem is that if D is large, think of the microarray data. D is several thousand, and to look to try every subset is too expensive. So therefore, this approach, which has no complexity to the D's power, but only D square. Why D square? Why is the complexity D square? Actually, D square is the number of iterations, a number of evaluations of the error. The complexity is much higher. It depends also, of course, on the number of our observations. I mean, capital N. Yes, capital N. So, but why O D square? So for selecting one feature, we must try all D of them. For selecting second feature, we try D minus one of them, and so on. And in worst case, if the number of selected features is big, it could be big O of D square. Of course, usually set in advance that we will not select at most D features out of the D features, but we say we would like to select at most 1/2 of the features or 100 of the features from constant. So this will be better. The symmetric approach is backward search. Backward search means that we start with all the features, and we try to delete one of the features one at a time, and we work in similar way as the forward search. So we delete one feature, compute the error, and we select such feature which causes increase in the error, the smallest increase in the error. And floating search is a combination of both forward and backward search. We usually use two constant KRL, and in one phase of the computation we add K features to F and remove L features from P. So F and P, F will be a set of features we would like to have there, and capital P is the set of features we would like to remove. And step by step, we increase the size of F and increase the size of P until we examine all the features, and then we stop. Questions? I think that these algorithms are pretty easy. So let us continue with a more complicated approach. And I must say, I would like you to know the derivation for the first principal component. How? So, is here anybody who has not heard about principal component analysis, PCA? Everybody knows. So this should be pretty simple for you. Okay. So the goal is to find a transformation which transforms the original vector of one observation into a vector with smaller number of dimensions, smaller number of elements, and the transformation should be linear. So we are looking for a linear transformation. So if we would like to compute the first element of the target vector, so if this vector should be mapped to this one, we would like to compute the first, and this should be a linear combination. What does it mean, linear combination? So we take the elements of the vector, and each element of the vector x, we multiply by some constant, and we sum them together, and this will be the value for the first coordinate of the vector after the transformation. So the transformation can be described by one vector w sub 1. And the transformation can be mathematically written by w sub 1 transposed times x. Why w sub 1 is transposed? It's because if we consider vector, by default, the vector is a column vector. And here we multiply two vectors. So we actually would like to compute the dot product. So the column vector W is transposed. So we have row vector times column vector, and we can use matrix multiplication, and the result is the dot product. So this is how to compute the first coordinate, and the goal of principal component analysis is that we should select the weight vector W1 transformation such that the variance of Z is maximized. Why to maximize variance of Z? Z is the first component here. Why to maximize? So we would like to store most of the information from the initial space in the resulting space after the transformation. So we would like to obtain such mapping which will preserve the distribution of the data. And if the transformation is not very good, then it will map all the data to something where the resulting values for this coordinate, for the first coordinate, will be very similar. And therefore, we lose information. So we would like not to use the information. It's not a whole story about that. So just to review, the mean value, so expected value of x is the mean. We can compute easily the approximation using mean, and variance variance of the data is the expected value of x minus mu minus the mean, or the expected value squared. So that here it is computed as a row vector x minus mu times x minus mu transposed column vector. So when we multiply them together, we can do that. And the result is the covariance matrix. Variance for Z is just one number. because it's one number, we need not to use covariance metrics to compute its variance. Variance of z is expected value of z minus the expected value of z squared. Okay, so our goal is to maximize the variance of z. So this we would like to maximize. And let us look at the derivation of that. So z is w sub 1 transposed times x. So it's substituted here. Next, we use the formula for the variance. So we have w sub 1 transposed times x minus the expected value of the same and the whole squared. In order to obtain squared, yes. What is the expected value of W1 transposed times X? So W1 transposed is a vector, one vector. So the expected value is, of course, the vector. We can pick the vector out of the expected value, and expected value of x is mu. So this is the first transformation, and we have here the difference and squared. Okay, in order to obtain this square, we can just multiply W1 transpose times x minus W1 transpose times mu. This is times the same. And now trick is, if we have a scalar value, one number, we can transpose it. And if we use the transposition, so this parenthesis can be transposed, because it's just one real number. Transposing real number doesn't change it. Okay, so from the first parenthesis, we can pick W sub 1 transposed in front of a parenthesis. So we have W sub transpose times x minus mu. And we can take the same, but transposed. What does it mean? If we transpose a product, this is product of transposed elements, but in opposite order. So we will have W sub 1 transpose times x minus mu times x minus mu transpose times transposition of W1 transposed. This is just W1. Okay, what we have here, W sub 1 transposed is a vector of constants. So we can put it out of the expected value. Similarly, this one, but to the right. So we have here W1 transpose times expected value x minus mu times x minus mu transpose times W sub 1. And what we have here inside is exactly the formula for variance for the covariance matrix. So the variance of Z is W sub 1 transposed times the covariance matrix of X times W1. This is not the end, of course, of the story. In general, we will compute such a vector W1, which maximizes the variance of the resulting value. But then we will add another vector W sub 2, and we add altogether some k vectors when we compute transformation into k-dimensional space. Okay. But we will return to the computation of the first value of the first weight vector W sub 1. In general, when we have all these transformation vectors W sub 1 till W sub k as column vectors put in a common matrix W, we can express the transformation, and Z is now not the first coordinate but all coordinates. like W transposed times X minus mu. Let us return back to the first component, W sub 1. So variance of the transformed value Z is W sub 1 transposed times the covariance matrix of X times W sub 1. If we would like to maximize the variance, we can do that very easily. We can multiply the W sub 1 by some big constant, and we increase the variance. So this has no there is no reason for such. So instead we require that the norm of the vector W sub 1 is 1. And what we would like to obtain, we would like to maximize W sub 1 transpose times covariance matrix times W sub 1, with the constraint that the norm of the vector W sub 1 is 1. It's bad. We would like to maximize, and we have some condition, and there is a method called Lagrange multiplier method, how to solve such maximization. And actually we will just compute maximalization without any constraint, and the maximalization is based that this condition we include in the objective function by some constant alpha. For that we require that it's positive, times W sub 1 transpose times W sub 1. What is this? Is the norm squared. Norm of vector W sub 1 squared minus 1. By why minus 1? Because if this parenthesis will result in 0, then if it is multiplied by alpha, then this will not change the maximal value of the first term. If the result of this parenthesis is different from 1, what are the possibilities? So if it is different from 1, we will subtract alpha times the difference, and this will result in lowering the maximum. So this is the idea of the Lagrange multiplier method. I am not going to prove the correctness of the Lagrange multiplier method.
It seems like quadratic programming problem. Is there a reason for using the Lagrange method and not some
It's easy, as we will see that so we would like to maximize this function, and for that, of course, we use the analytic method that in order to obtain a maximum, at the maximum the derivative should be 0, but derivative W sub 1 is a vector, so all partial derivatives according all elements, constituents of the vector W sub 1 should be 0, and this is the result of the derivative. My personal experience is this, that usually students look at the function. This is something like sigma times W sub 1 squared. So the derivative would be 2 times constant, the covariance matrix, times the original vector W sub 1. So this is this term, minus alpha is a constant. So alpha, here we have again W sub 1 squared. So the derivative would be 2 times W sub 1. times and alpha is from this term, the derivative will be 0, so we obtain -2 alpha W sub 1. This is correct, the result, but the explanation is not fully correct because we are computing many derivatives at once. I have prepared a slide with the explanation to be sure that I cannot. Click it. So we are computing the partial derivatives of W sub 1 transpose times the covariance matrix times W sub 1 minus alpha times W sub 1 transpose times W1 minus 1. And partial derivatives for each element of W sub 1. So W sub 1 has element 1 to D. D is the number of dimensions in our observations. So how it looks like. So here we have actually product W sub 1 transpose times sigma times W sub 1. And the derivative of the product would be derivative of the first part. So this is the partial derivative of W sub 1 with respect to the eighth element of W sub 1 times sigma times W sub 1 plus W sub 1 transposed times the derivative of sigma W1 according to the eighth element of W1 minus alpha is a constant, so I can take it forward and compute derivation inside. So from this term, I will have no value 0. So just from this term, and this will be again product. So partial derivative of W sub 1 transpose according to the eighth elements of W sub 1 times W sub 1, and here symmetrical. Let us look here. So here we have the partial derivative of W sub 1 transposed with respect to an ith element of W sub 1. So all other elements of W sub 1 will result in 0 derivative, 0 value for the derivative. So we obtain just a column vector. Oh no, W sub 1 is a column vector, so we have row vector where we have all zeros except the eighth element, which will be derivative of W sub 1i according to W sub 1i, so this will be 1. And similarly, we will is the case here. And here I have, yes, this is the same partial derivative of W sub 1 transposed according to the eighth element. So it's row vector with single 1 at eighth position. And here it is the same, but only as a column vector. So if we compute that, here from this, we obtain just the ith element, ith row of the matrix sigma times W sub 1. Sigma times W sub 1 is actually vector. And we pick just the ith element of that. So this is what is computed by the ith row of the covariance matrix sigma times the vector W sub 1. So it is here. And similarly, W sub 1 times the ith column of the covariance matrix, but we know the ith column and ith rows of covariance matrix are the same because it's symmetric. Minus, and from here we have alpha times the same, 2 times the ith element of W. So altogether for the ith, so the derivation according to the ith component of W sub 1, we obtain 2 times product of the ith row of the covariance matrix times W1 minus 2 alpha times W sub 1 ith element. This was for the ith element. We will need to compute the partial derivatives for all dimensions, all the dimensions. We can put them together and we will have exactly what was on the previous slide. 2 times covariance matrix times W sub 1 minus 2 times alpha times W sub 1. So even if we work with vectors and matrices, because there was the matrix for the covariance matrix, we have here this equation. So this should be 0. So from this we have that if we divide by 2, we obtain that sigma times W sub 1 should be alpha times W sub 1. And this means that W sub 1 is an eigenvector of matrix X. Because if we multiply the covariance matrix by W sub 1, we obtain some constant alpha times W sub 1. Okay, let us continue. We would like to maximize the variance. So what is the value for the variance? The value for the variance is W sub 1 transpose times sigma. Now we know that sigma times W sub 1 is alpha times W sub 1. So we obtain alpha times W sub 1 transpose times W sub 1. And we have the assumption that the norm of the vector W sub 1 is 1. So here we have the square of the norm, it's 1. So the result is alpha. So the variance is alpha. The variance is the eigenvalue of the eigenvector W sub 1. We would like to maximize the variance, so we select the eigenvalue, maximal eigenvalue of the covariance matrix. So it was a little tedious, but the result is that if we know how to compute the eigenvalue for the matrix and eigenvectors, we can obtain the transformation and we know how to compute it. So the lambda 1 is the eigenvalue maximum with largest eigenvalue for the covariance matrix. This was for the first principal component. For the second principal component, we would like to maximize the information. So the transformation according to the first principal component will transform each of these vectors in one coordinate. And we would like to add a second coordinate. So one coordinate is for the distribution along some line. And the second coordinate will be distribution on different line. And how to maximize the information if the second dimension in which we have is orthogonal. So the second principal component will be orthogonal with the first one. So we would like to obtain second vector W sub 2 with a norm equal 1, such that the transformation will be symmetrical, will be W sub 2 transpose times the covariance matrix times W sub 2. And the conditions are that the norm of the new vector should be 1. So this was used here. Again, we use the Lagrange multiplier method. And the second condition is that W sub 2 should be orthogonal with W sub 1. So the dot product W sub transpose times W sub 1 should be 0. And we can again use this Lagrange multiplier. So beta is some positive constant, and the contents of this parenthesis is such that it will be 0 for the desired property if W sub 1 and W sub 2 are orthogonal. we have already seen this one, and this is for the second principal component analysis, second principal component. So we would like to maximize this, this expression. Again, we compute the derivative according to all components of W sub 2. And the derivative will be a little longer. So 2 times from this, we obtain 2 times covariance matrix times W sub 2. From this, we obtain minus 2 times alpha times W sub 2. And from the last parenthesis, last term, we obtain beta times W sub 1, because we compute derivative according to W sub 2. This should be 0. So if we set this to 0, then we can use the properties. So we know that for when this is maximal, then the values for these 2 parentheses should be 0. So W sub 1 transpose times W sub 2, they should be orthogonal. What will be the value for this? 0. For W sub 1, we know that the norm of the vector is 1. So this will simplify to 2 times. So from this, we have W sub 1 transpose times the covariance matrix times W sub 2 minus beta should be 0. And again, if we compute yes, so this is scalar value, of course, and we have that W sub 1 transposed times the covariance matrix sigma times W sub 2 can be expressed as in this way. What is this way? I transposed. I use transposition. If I use transposition, I reverse the order and transpose each element. So W sub 2 will be the first and transposed. Sigma should be the second and transposed, but the covariance matrix is symmetric, so the transposition is the same. And W sub 1 will be the last one, and transposition of W sub 1 transposed is just W sub 1. We can do that because the value is just scalar, that's the one real number. And that we know that W sub 2 transpose times W sub 1 is 0. Why? This is one of the conditions that they should be orthogonal. So so the result will be that we obtain sigma times W sub 1. Sigma times W sub 1. This was the first the eigenvalue lambda 1 times W sub 1, and therefore so this will be here, and the eigenvalue I can put in front, and here I have the product of orthogonal vectors, so I obtain 0. Now we can return back to this formula because now we know that 2 times sigma W2 from what is the value for beta? Here we have shown this term W sub 1 transpose times sigma times W sub 2, it here is 0. So beta must be 0. If beta is 0, substitute here, so this term we can omit, and we remain with the first two, and we have that sigma times W sub 2 equals alpha times W sub 2. In other words, W sub 2 is also an eigenvector of the covariance matrix sigma. And we would like to have as much information preserved. So we would like to maximize also the covariance in the second coordinate. So the variance in the second coordinate. So therefore, we select the second largest eigenvalue for the covariance matrix. And similarly, we can continue. We have still a little time. So what is done using the principal component analysis? If these are our original data, then we actually find a direction in the data which preserves the most of the information with the highest variance. And this will be transformed into the first coordinate. Then we select some orthogonal axis and look for such axis which will maximize the variance of the values on the axis. And this will be made out of that. We make the second coordinate after the transformation, and so on. So the transformation is that we have the matrix W and transpose times x minus mu. So from the original data, we subtract the mean. So actually, we will move this center to the origin of coordinates, and then we will rotate the data in order to obtain this transformation. So this is the transformation, and usually we use only several dimensions for the transformation. So we use just k dimensions. How to select k? If we have the eigenvalues lambda I of all eigenvalues of the original covariance matrix, then the value of the sum of the first k largest eigenvalues divided by the sum of all eigenvalues is called proportion of variance. And this is usually used as the measure of information preserving, how much information is preserved after using just first k principal components. And here you can see the eigenvalues. So this is the largest, and then they step by step they decreasing. And this is the proportion of variance. And of course, if we use all d dimensions, we obtain the proportion of variance equal 1. But usually we set some level, for example, 0.9 for the proportional variance, and we cut the number of used principal components to some lower value. In case of visualization, we would like to obtain just 1 or 2 dimensional data, then we use just the first 2 or first 3 principal components. I have still 5 minutes. This is a result of an artificial data. This is not from bioinformatics. This is the set of handwritten digits. So you know about the NIST. So this is some variance of NIST. And if we use the principal component analysis and map the data into the according to the first two principal components, we obtain mapping in a plane, and here is the result. If we look at the resulting, there are for some values are also labels there, and we can see, for example, mapping of digit 7, they are all close together. Mapping of digit 6, they are also close together. But there are some digits which are mapped to regions where they are mixed. Can you say me some digits? So it would be nice if after the transformation we obtain separate regions for different digits, because then we can use just these two dimensions for classifying the handwritten digits. But it doesn't work with two dimensions because yes. So nines, for example, here we have nines, and there are among 4s and 1s even, and here are close to 7. So it's not enough to represent the handwritten digits just by two by transforming the original. What is the original vector? Original vector is I take a vector, and in each position of the vector I put the gray level of 1 pixel of a picture of the digit. And I suppose I will not do the factor analysis now, because I would need more than 3 minutes. Last week I take more than assigned time for the lecture. I will leave it for the next lecture. So in the next lecture, I will finish the method for dimensional direction, and hopefully we will move further. Thank you very much. Just one information: the method we have seen today at the beginning, approximating the density function using kernel functions. This will be actually in the first assignment for you. I will describe it in the lab next week. Thank you very much.